And so today's topic with statistical hypothesis testing is, I mean, it has all kinds of great things in it, just that name. I mean, you got statistics, which many people are afraid of, okay? And then you have hypothesis, which everybody associates with the scientific method. And so, I mean, you're really doing science when you're doing statistical hypothesis testing. Okay. And we'll talk this morning about how, or what is unique about an industrial lab environment. Okay, for this whole educational career, you've been doing your own results. You've been analyzing your own data, and it's been an individual case, right? You're in charge of your stuff. You get your business done, and you're fine. You've never really cared whether the person next to you was as precise as you are. I mean, maybe for your grade, right? But in an analytical lab, a commercial analytical lab, and even if you're working for the state, it's still a commercial analytical lab. You do analyses, and your client is the state or the federal government. I mean, you have stakeholders, and you need to make sure that it doesn't matter if I give the sample to you or to you, right? Because it's the lab's results. And so now it's not just whether you're doing your job, it's the lab doing its job. And so today's exercise, we're going to teach statistical hypothesis testing, but using a special example where an analytical lab is analyzing two persons' results to see if it matters if I give this sample to person A or to person B. In this particular case, we have a forensic chemist that's been there for years and has some experience, and we have a trainee coming in. And so you would expect that there might be some retraining or some growth that could exist in that trainee to make them as precise and as accurate as the forensic chemist. Okay, hello. Spelling almost. Okay, it worked. And so let's begin before we get into the statistics. Let's talk about hypothesis testing and error types. And so we have a peculiar language that we use in this area. We have the null hypothesis. Null is another way of saying zero. So the default hypothesis, H0, and that's called the null hypothesis. And all we can do is accept that hypothesis or reject it. Or even, we don't even say accept it, because to accept something would be to have some proof that it's true. And the null hypothesis is an assumption. We can't really prove it, but we can reject it. And so our terms are, we either reject it or we fail to reject it. Notice how we're not accepting anything. We're not saying anything is true. We're saying we either reject it or we fail to reject it. So that null hypothesis is our baseline assumption. And so in this table, in the two columns, those are the only two things that we can do. We can either fail to reject the null hypothesis, which some people would say we accept it, or we reject it. Now on the rows, that's the true situation. And unfortunately, we can't know the true situation. Now we can use standards, and we can kind of set up a situation where we know those, but in general, for an unknown sample, we don't know whether the null hypothesis is true or not. Okay, we can just look at statistics and either reject it or fail to reject it. Okay. So we're going to be in one of those two columns. Batteries are giving me fits today. Okay, let's go with this. And so the coefficients, this is examples of null hypotheses. We've done ANOVA analysis of variance. We get that table, and we have a coefficient for M and a coefficient for B. Same thing with a trend line. You plot a linear line through your data, and you get an M and a B value. And the null hypothesis for those is that the M and B value are not statistically significant. It's kind of a strange one. I mean, but that's our null hypothesis. Another way to state that is that M and B are caused by random fluctuations in the data. So our null hypothesis is that there's no trend in the data, and that we can do a linear fit, and we'll get M and B because mathematically we're going to have some values for those equations, but that their uncertainty would be huge and there really wouldn't be any statistical significance to M or B. Okay, so that's our null hypothesis. And then we would look at the p-value columns. Remember doing that in PChem? You look at the p-value, and that's the significance or the probability that that null hypothesis is true. And you want a tiny p-value. A tiny p-value means that the M is significant and B is significant. So we'll get into that some more later. Another null hypothesis, the data distribution is Gaussian. Gaussian is another term we use for random. So we would say the data is randomly distributed. It has a Gaussian shape to it. It's a normal distribution. So that might be a null hypothesis, and we'll see that tested in some of our analyses. Here's for today's examples. The trainee and forensic chemist data sets are from the same population. So we've taken our standard, we've made up some stock solutions, and we've taken aliquots out of that. And so we've given the samples to the trainee and samples to the forensic chemist, and our null hypothesis is that they're from the same population. And so that they should have the same mean answer. So, you know, each analyst is going to get different results every time they analyze it. But the mean of both of those should be the same. So that would be our null hypothesis, that the means of the two data sets are the same. Another way to say that is that the data sets are from the same population. So they have the same mean. And then another null hypothesis might be the trainee and forensic chemist data sets have the same variance. Remember, variance is another word for standard deviation. It's standard deviation squared. So saying they have the same variance means they have the same uncertainty. Notice how that's totally different than accuracy or the same mean. They could have the same mean and different variances or different uncertainties. Or they could have the same uncertainty but different means. So those two things are independent. The whole peak could shift left or right, or the peaks could be narrow or fat. Okay, so those are two different things. And just like Aristotle said, if you say that it is, and it is, that is true. And if you say that it isn't, and it isn't, that is true. Those are the two green squares up there. If you fail to reject HO, and HO is reality, is true, then that is true. You've made a correct answer. And if you say that it isn't, and it isn't, then you're correct. But if you're wrong, if you say that it isn't, and it is, then you've got a type 1 error. And if you say that it is, and it isn't, you've got a type 2 error. So if you reject the null hypothesis, but you should have failed to reject it, then you've made a type 1 error. Now we can't necessarily say which one is a false positive and false negative. That depends upon the particular application. But one of those will be a false positive, one of those will be a false negative, depending upon how you've set up the test. Okay? So if you're trying to test for a particular drug, a substance of abuse, or something like that, and one of those will become the false positive, one of those will become the false negative. Any comments so far? Have you covered this in any other class? What class? Was it a forensic science class or?
Did we learn stats? Yeah, we're learning on stats right now.
Okay, so tell me about the stats course that y'all took. What part of the degree was it in? Was it in?
It's an elective for us, and it's required for everyone below us.
Yeah.
And it's required
Yes.
to get a job. So.
Yeah.
Yes, and so that's the new change. And so before this transition, this was the main stats that y'all were getting as part of your degree. It was this first third of the course. Okay, so now you're having to take a particular course in stats. Where is that being taught? Is it in math or is it in forensic science? So is it applied statistics?
It's math.
It's in the math department. Okay, yeah. Okay, well that's good. I mean, it's going to make you better. Okay, so just trying to see the lay of the land. So let's look into this now. So decisions on the null hypothesis. We talked about that p-value in Excel in the ANOVA table. And so the first column is your coefficients, the second column is the standard errors, the third is a t-value, which is used to calculate the p-values. And so that fourth column is the p-values, and p stands for probability. It's the probability that the null hypothesis is true. And so if you want a linear fit where you've got good statistics on M and good statistics on B, then you want those to be statistically significant. So the null hypothesis is that they're not statistically significant. So you want a really low probability that they're not statistically significant. Okay, so a lot of double negatives here. So if the probability of the null hypothesis is really low, like less than 0.05, then you reject it. In other words, if the probability, I just said that in English, okay? It's written mathematically and then you have the English translation. And so this 0.05 is called your alpha value. So that's an important piece. You'll hear that, they'll say with an alpha of 0.01 or 0.05, you have to describe what level of scrutiny you're applying to your null hypothesis. You might hear about confidence. Well, 1 minus alpha is your confidence. So if alpha is 0.05, then you're operating at 95% confidence. And then this is the main point really of today. If you can't state your null hypothesis clearly and concisely, then you have no business doing statistics. Okay? Because that's the first thing someone should ask you. When you say this linear trend was, applied to the data, you start talking, and then someone raises their hand and says, well, what kind of confidence do you have in that intercept? And if you don't know, that's just because you haven't done the statistics. But if you say, well, it's statistically significant, and then they say, well, what was your alpha? What level of confidence were you using? And, you may get into trouble if you haven't thought about those things. So you really need to follow through on your data to make sure that you can provide p-values for B and p-values for M if you're using a linear fit. Okay? And that you can state your null hypothesis. Because again, that's going to be a real easy way to attack your results if you don't understand the statistics behind them. Okay? Doesn't mean they're invalid. It means that you have a lack of knowledge and your credibility just dropped. Okay? So you don't want that. So this is all based upon the Gaussian distribution. There may be corrections for other kinds of distributions. I'm just not aware of them. That would be a math question. Go to your math stats professor. But all of the ones that I talk about are based on the Gaussian distribution and the area under that curve. And so we'll be thinking again about if this is the distribution of your data, 99.7% of your results will fall within plus or minus 3 sigmas. So coming up with these confidence intervals, we don't always have a population. Sometimes we just have a sample where we've taken 3 measurements or 5 measurements. And so in those situations, when we have a sample, we have to use the t-values to come up with our confidence intervals. I remember doing this when I was in quantitative analysis. We would do 3 titrations, and we were asked to give our 95% confidence intervals for the concentration of our acid. And we had to use this t-table, which we had in a book, but you can actually generate this table in Excel. And so I've given you in the notes the formulas for these t-values here with this. So you've got that column and the rows labeled, and so here we have the t inverse, which will give you all of these t-values based upon the degrees of freedom, which is up there at the top, or the number of samples, actually 1, 3, 5, etc. And then 1 minus A10, so the A column, those are our confidences, so 1 minus that would be our alpha value. So the t inverse takes in the alpha and the number of data points, and it will give you those different values. So how would we use this table? Let's say we did 3 titrations and we wanted to come up with the confidence interval for our concentration. It's this formula right here that we would say our mean is equal to the mean plus or minus this uncertainty. And so we had the standard deviation for our 3 samples, and we had this t-value, and divided by the square root of 3. And so for 95% confidence, that t-value is 3.182. Come over here, I did 3 titrations, I'm at 95% confidence, that's my t-value. So this is going to be 3.182 times s over square root of 3. And that will give me my 95% confidence interval if I've done 3 titrations. Now let's say we've got a calibration line, we've got actually a good understanding of our uncertainty, we can do propagation of errors, and because we've used that calibration, we're really confident that we understand the uncertainty in our system. And so we would call that sigma, and we could use just the z value here. So if we've done a calibration and we've calculated our uncertainty by propagation of error, using the uncertainty in M and the uncertainty in B, then that would go here. And our 95% confidence interval would be 1.96. And so you'll use 1.96 so often that you'll pretty much use it. It's not quite plus or minus 2 sigma. It's close. But to get exactly 95% confidence, then you use 1.96 of your sigma. And then those z values are given by this formula. So again, it's the normal distribution, but it's an inverse function. We're taking 0.5. Let me show you how this number is calculated. What we're giving it is 95% confidence. That was worse. That's better. We're saying I want to cover 95% of this area, okay? And it has a mean of 0 and a standard deviation of 1, okay? So that's our mean, that's our standard deviation. And I want to return this value, right, that contains 95%. Well, I start at negative infinity, right, and I start integrating. And where do I draw this line? Actually, only 2.5% is remaining on this end, right? Because 95% confidence is 95% of the middle area. And so there's 2.5% on the left and 2.5% on the right that I'm missing. And so I want to just find this point. And so this norm inverse starts out with 0.5 or a half. Remember, the area under this whole curve is 1. And so the 0.5 gets me to the middle, okay? And then I want to go further by my alpha over 2. So that A10, 95%, cut in half, okay? It's going to be 45. And so I've got 5% left. And the 0 and the 1 here give me the mean and the standard deviation. And so it's going to give me this value, which is going to be the 1.96 for the 95%. For 90%, 1.64. For 99.99, notice I have to almost go to plus or minus 4 sigma. So it's nice that we have Excel to do these inverse relationships for us, or we can also find them in tables pretty easily. So let's look at the personnel analysis. Let's take our trainee and our forensic chemist, and let's give them both a check sample of 13.2% cocaine plus or minus 0.1. So that's how well we know our standard, to 1/10%. And so each one of them gets 10 samples to analyze, and they all 10, we assume, contain that standard value of 13.2, and they analyze them. And these are their results. So you can see the trainee and the forensic chemist are all pretty close to 13.2. And you can see that, I mean, just looking at the data, this was really silly, but we use acronyms for everything. And when I was taking industrial statistics, they called this ANOG, analysis of good. So you just look at the data and decide, is it good or not? I mean, you don't have to get into the math yet. You just look at the data and say, does it resemble what we expect? We gave everybody examples of 13.2%. And unless you just look at the data, sometimes you can really waste a lot of time in realizing the data is not any good. Well, in this case, it's pretty good, right? You're looking at their results, especially the forensic chemists, they're all 13 point something. and they hover around the 13.2. And then look at the trainee. They did okay. You got some 12s, but they got some 15s. Already it kind of looks like the trainee is more scattered in terms of their results than the forensic chemist. It's sort of just a gut feeling at this point, though. It's really not been shown statistically to be true. But because we have some below 13 and some above 13, it looks like the trainee might be hovering around the true value or the accepted value. So now let's dive in and let's calculate some statistical parameters for these. If you were just given this data, before you go to the next page in the notes, what are some of the things that you could calculate? Let's try to list as many things that we can calculate about this data set. What are the obvious ones? Mean and standard deviation, okay. What's another one? So those are obvious.
You take the pooled standard deviation.
Yes, you could do the pooled standard deviation to kind of see how they both, like what's this uncertainty with both of them combined. Okay. T-test, we'll get into that, okay. But as far as just the data, before doing any statistical testing or hypothesis testing, what are some other figures of merit? So mean and standard deviation are good figures of merit.
Percent error.
Percent error. Well, yes, because we know the accepted value. So yes, we could take that mean and compare it to the accepted value. And that would be, some difference. And then you could see what percent of the accepted value is it. So are they 5% off or 50% off? So that's a good one. Range is another one. Okay, what's the range? That doesn't require any kind of, how long it took you to take the standard deviation, right? You got the column of differences, square them, add them together, all that business. We could just look at the range. So here we have a 15 and 11.5. Okay, it's a pretty big range. And over here we have 13.7 and 13.1. So 0.6 is the range for the forensic chemist. And was like, 3.5 for the, quite a bit different. 3.5% range for the trainee and 0.6 for the forensic chemist. And so this is what we've done here. This is just calculating a lot of different figures. We've got the mean here, 12.9 and 13.3. We did the percent error, like you said. Now, how do we calculate the percent error? It's important to get the subtraction correct, okay? And so, just like we were doing in our daily differences, if you're doing daily differences for your control chart, you can't just take the difference between the two or the absolute value of the difference between the two because the sign tells you something. And so, the trainee is 12.9 and the accepted value is 13.2. And so we see that the trainee is low. All right? So we want our error term to be negative. We want to see that our trainee is low. And so when you see a negative value, you think, oh, that's small, that's below 0. Okay? So we want that trainee value, the mean, to be, you want to subtract the true value from the trainee. Since the true value is higher, it comes out as a negative number. Okay. And so we have this C17, that's the trainee value or the forensic chemist value, minus the true value divided by the true value. And also you're looking at the denominator. You want the true value to be the standard. And so you're saying what percent of the true value is error in this case. And so they're low by 2.5%. And then the forensic chemist is high by 0.5%. You also have the absolute error, which is just the difference between the two. You're not dividing by anything. And so this is saying that the trainee is low by 0.33, and the forensic chemist is high by 0.07. Standard deviation of the samples. So this is using, because we only have 10 values, 0.93 is the sample standard deviation, 0.2 for the forensic chemist. They've changed these formulas a little bit now in Excel. This one will still work, but it's like standard deviation dot S for sample and standard deviation dot P for population. So if you're typing in the values ST, Excel will do an autofill, and you have two options, P and S. P is for population, and S is for sample. So that's another reason why I wanted to go through all of these, is so you have all of the formulas over here on the right that you can use to calculate these things. Then we have the RSD. So this is, again, the standard deviation divided by the mean. So we have a 7.2%, it's really coefficient of variation, and 1.5% for the forensic chemist. So you see right there, quite a bit of difference. 7% versus 1%, 1.5% in terms of their relative standard deviation. Just to show that the sample standard deviation is a more conservative estimate, I went ahead and calculated the population statistics. So it's 0.88 if you use the population standard deviation, and 0.93 if you use the sample standard deviation. And so that's why we say that sample standard deviation for a low number of data points, like 10, is more conservative. It gives a wider error bar so that you're more confident to capture the true value. The variance is just those standard deviations squared. Here's the range, 3.5 versus 0.6. And then the confidence interval, or confidence level, using those t-value equations is here. So this is the 95% confidence interval range. So the confidence interval goes from 12.2 at the low end to 13.5 at the high end. And so you can look at this confidence interval, and the trainee, if they did not know the true value, they could still calculate this confidence interval, because all they need is their mean and standard deviation. And they would say, I believe that the true value is between these two limits. And it is. It goes as low as 12.2 and as high as 13.5, and the true value was 13.2. So even though they're low by 2.5%, the precision is such that they still captured that true value. Now the forensic chemist, they also have a 95% confidence interval here. The low end is 13.1 and the high end is 13.4, and they do capture the true value. But they're also a very narrow range, and it's still very good. They capture the true value and they have a narrow precision. Any comments on any of these? We captured all the ones that we came up with and a few extras. Now let's look at some of the hypothesis testing. We've really got 4 main tests that we've done on this data. The top 2 are outlier tests. One is the Grubbs test, the other is Dixon's Q test. And then we have the test for equal means. In other words, are the distribution of the trainee and the forensic chemist the same? So if you were to show the 2 plots of their data, do they overlap, or are they like this? And then the F test for equal variances is one narrow and the other one wide. So you're just looking at the variances in the data. And that one you can kind of tell is probably going to come out that they don't have equal variances, because the forensic chemist data is so tight and the trainees data is so spread out. Okay. So we'll come back to these. These are the formulas for all of these, but let's go through these tests. So the null hypotheses that we have in this analysis are that the trainee and forensic chemist data sets are from the same population. Okay. When we do this, so we can look at the results here, the same population would be the t-test. In order to do that t-test, you need the pooled standard deviation. And then you calculate the experimental t-test for this data. And here's the formula over here. We'll see a better view of the formula in a second. And then you have the table data. And so if your t-statistic is less than the t-table, the means are from the same distribution. If the t-value is greater than that t-table, then they're from different distributions. So let's look at the t-test. Let me skip past this for a second. So here's the t-test calculated for the data. And so we're looking for equal means. And so we have the mean for the trainee and the mean for the forensic chemist. It's divided by the pooled standard deviation. And this is kind of like a reduced number of degrees of freedom here. It looks like a reduced mass. And then the pooled standard deviation calculation is shown here in this equation. And so you calculate this calculated or t-calculated value and compare it to the critical value for the t-tests. Notice how if the difference in means is 0, then the t calculated will be very low. It's not going to be greater than the table value or the critical value. But if the difference in means grows and is far apart, then the t calculated gets high, and eventually it triggers and says, yeah, the null hypothesis that they're the same is rejected. Here's the F-test for equal means. It's an example from, again, from one of those, or no, the t-test for equal means, sorry. This is the example shown in the book, the Bell book. And once again, that if the t calculated is greater than the t-table, the null hypothesis is rejected. Let's go back to our values here. So we calculated a t-statistic here. It's the absolute value of the difference in means times that square root of the reduced sum of those data points, and then divided by the pooled standard deviation, which we calculated up above. This is the t-inverse function that gives us the critical value for 9 data points, or 9 degrees of freedom, and 0.025. Remember, we're operating at 95% confidence, and so we take that alpha of 0.05 and divide it by 2, because we could be off on the high side or on the low side. And so we're looking to see where it exits that middle shaded area on either the high side or the low side. And so that's our t-critical value. So our t-calculated compared to the t-critical, our calculated is less than the critical value. And so the null hypothesis that the means are the same, we fail to reject that. Same thing for the F-test. The F-test for equal variances, we take the variance ratio, so C23 and D23. Let's go up here. C and D23. So here is C23 and D23. So we take that ratio of the variances. Now, what is that ratio going to be if the variances are equal? It's going to be 1. And so we're trying to see how far away this is from 1. So we take the ratio of the variances. If it's really high, okay, then we'll have a high F number. If it's really low, the denominator is huge, we'll have a really low F number. So we have to test for high or low in this particular test. And so we have a critical F value for the low situation of 0.25 and a critical value for the high situation of 4.03. And our ratio is 21.39. Okay. So our trainees' variance is 21 times the forensic chemist's. And 95% confidence. This is saying that there's a 5% chance, or really 2.5% chance, that it would be as high as 4. If they had the same standard deviation, then there'd be a 2.5% chance of random variation throwing it above 4, that ratio. And our ratio is 21. So definitely different in terms of variances. So because our test value is 21.39 and our critical value is 4.03, our F is much higher than the upper critical F value. Therefore, the hypothesis that they're the same variance is rejected. Looking at our data up there, notice the forensic chemist, the trainee has one data point that's kind of off. It's 13s and 12s, and then you get down to the 9th data point is a 15. So they might have an outlier, which is throwing their variance off. 21 for an F test is huge. So what's really going on with the trainee? Maybe they had, one piece of glassware that was dirty, or some kind of thing that they didn't notice that threw that data point off. So we can test for outliers, and there's two ways to do that. In the analytical text, Skoog, West, and Holler, they had this Dixon's Q test. And then there's also the Grubbs test. I show both just because they both still show up, but the Grubbs test is more popular now. So the Dixon's Q test is going down in popularity, and the Grubbs test is going up. Okay. So let's look. So far, we've said that the trainee and the forensic chemist data sets are from the same population, and we failed to reject that because of the t-test. And then we said that the trainee and forensic chemist data sets have the same variance. So that's our null hypothesis. We did reject that one using the f-tests. And so let's look at our outlier test. So this is the Dixon's Q test. And we have a questioned data point. That's what I mean by X question mark. So that is the 15. That's sample number 9. And then we have a nearest data point. So we would look at the data and find the data point nearest to 15. And we would calculate that difference. And then we would look at the range and calculate the range. And so what we're asking is how much of the range is made up by this one wonky data point. So if you have a number line, okay, which one of these is good? I'm going to throw it away. That's not it. Can you throw that one away for me? So if we have this situation, we're asking to take this gap and divide by that gap. And so this is X question mark, this is X near, and this is the range, or max minus min. And as this gets closer and closer to 1, then you're getting closer and closer to having an outlier. And how would it be 1? Well, let's say you had 3 identical measurements where your 3 measurements were right on top of each other, and you had this one over here. Well, your nearest one is there, and your range is there. So that's definitely an outlier. You got 3 of exactly the same answer to your measurement devices, the number of decimal places, say on your balance or something, and then you got one that was way off. Okay. Now this can also kind of give you a false result if your balance doesn't give you enough decimal places. Are those really the same exact measurement? No, it's just the readings are the same. And so you'll almost always get, well, you will, in terms of Dixon's Q test, you'll always get an outlier if your balance or whatever you're using to measure coincidentally gives you just the same reading, because the questioned distance is always going to equal the range. So that's a weird case where you can be fooled, and it's really just because your measurement device doesn't have enough digits displayed to show the true differences between the samples. And so another thing that's an important point, and that is you only use these Q tests or outlier tests in situations where you have no reason to reject that sample. So if you spilled a little bit of your sample, throw that one out. You don't need to use the statistical test to tell you that's going to be suspect. If you're, shaking the vial and you look in there and you see, it's behaving differently, like the vial's dirty, the water's beating up on the glass, and on the other samples it doesn't do that. Like, okay, this vial is bad. I'm gonna get rid of it. Okay. So if you observe something, you're a scientist. If you observe something significant, you don't need to wait to let the statistics tell you that that's a problem. Okay, make a decision. This is only for those cases where, for as far as you could tell, every sample was the same, everything was behaving well, the instrument was running well, there were no power glitches or anything like that, and yet you've got a 15 and all your other data points are 12 and 13. And so you look at it and say, what's going on with the 15? And so we can take this Q experimental and compare it to the Q critical, and once again, if the experimental is greater than the critical, then that null hypothesis is rejected. The z-test, this one is recommended now by the standards organizations like ISO and ASTM. And this one is, I guess, more closely tied to the Gaussian distribution. And so it's comparing it to a Gaussian distribution with a mean of 0 and a standard deviation of 1. And it's trying to find out, where the question data point lies. If your question data point lies above, 1.96, then it's going to be less than a 2.5% chance of being that high. Okay. And so it's likely an outlier. And so this is how you calculate it. You take that questioned value and subtract the mean and divide by the standard deviation. So subtracting the mean essentially moves it over to where you're comparing it to the mean of 0, and dividing by the standard deviation sort of counts how many standard deviations it is from the mean. And so it's, again, used if there's no known reason for rejecting that data point. And the null hypothesis is that it's not an outlier, but if z question mark is greater than the z critical, the z table, based upon your alpha value, then you reject H0. So let's go back and look at our data points in this table. Here we go. So we calculated the Grubbs test on sample number 9, and it came out to 2.3. So it was over here at 2.3. And for 95% confidence, our value was 1.96. Okay. If I'm right at that point, okay, it's like a 2.5% chance that I'd be at that point. If I go further, there's a much less of a chance. And so there's really a very small chance that I would get a data point this far out if it was randomly distributed. So we're saying, was this 15 just random variation? No, it wasn't. I don't know what pushed it that far out, but I can say it's not part of the population of randomly distributed data. Something significant happened to that sample. And so I can throw it out because it doesn't represent the mean. Okay. Same thing with the Q test. We calculated that that question distance was 4.86. The critical value was 0.466. 0.486 and 0.466. And so also it's greater than the critical value, so it's rejected. Now, if you wanted to, then you might go back through and calculate now for the trainee all of the data points and statistics for the remaining 9 samples. And so then their variance would drop, their mean would shift a little bit, and so on, because you've rejected that outlier. And then you might see that their variance was much more similar than it was with the outlier. Okay. One thing that we haven't addressed in all of this, why 10 samples? It's a question no one asked, right? And I'm not fussing at you, I'm saying just that's the way the system was set up. But how would you decide if 10 was good? What about 5? What about 15? Go ahead.
It's supposed to be like 10% of the overall population, or like n equals 30 or 1.
Yeah, there are some ways to come up with the number of samples that you need to run. Okay, and this was a question that was never answered in my chemistry training. It drove me crazy. You know, we would do 3 titrations or whatever. And mostly it was just driven by time. But I never understood what, you know, I knew 5 was better than 3, but I really didn't want to do 5 titrations. You know? Yeah, and so it was sort of a tolerance thing too. Is like, can I tolerate 5? No, but I can 3. Okay, but that's probably not a good answer, right? It's not tied to the precision of the data. I know 5 is going to be better, but that means 10 would be better than 5. But 50 would be better than 10. If I really want to know the data, then, you know, how do I decide? And so that's the sampling plan. So that's the last thing we'll cover this morning, is related to this forensic chemist and so on. So this is the sampling plan. And there's the GUM, the GUM, okay? The GUM is the Guidance for Uncertainty Measurement, or Management. Guidance for Uncertainty Management. The ASTM also has sampling plans and sampling guides. Okay. And so the first thing you do when you get, you know, a seizure or some kind of sample comes into the lab is, most of the time it's however it was shipped or collected, right? So it's wrapped up and so on. You inspect it, you catalog it, you write everything down, all the descriptions and so on, but it's not really ready to analyze. I mean, you can't just, you know, typically take it and put it right on the GC. You need to dilute things, you need to set up your standards and so on. So how many lab samples do you take out of a bulk object? And that's the question that Guidance for Uncertainty Management answers. And so you decide on the number of analyses that you want to do. Now, ASTM E122 talks about the acceptable error and the expected uncertainty in the sample, not the instrument. And so this, to me, is difficult. They have ways to manage, but it's very difficult, though, to look at a sample and decide what kind of uncertainty you're going to have, especially if it's a white powder. I mean, you know, these little packets of white powder, you have no idea whether they're all the same or if one has more cocaine in it than the other. What are you analyzing? You know, what if it's not cocaine? What if it's some kind of other meth or something else? You know, what kind of uncertainties are you going to have in these samples? So it's very difficult to understand how you would come up with that sigma in this equation. But if you do understand, you know, the uncertainty in the samples, then you could actually solve for the number of samples that you need to take. And so that's what this N is here from the ASTM. Okay. Or if you wanted to use, instead of the uncertainty in the sample, you could use the coefficient of variation in terms of percent. But I think a more manageable method is this line here. This is going to be a conservative sampling plan. Now, what does that mean? It means it's expensive, okay, but it's safe. So what do I mean by expensive? You're going to sample more samples than you really need to, but you're not going to go crazy, okay? So this says if you've got 20 packets, then you're going to sample all of them, okay? Because again, you've got an auto sampler tray and so on. You can make up 20 samples. You can calibrate the thing, load it up, and it's not a problem to sample 20 packets. But But you get up to 25, 30, 100, what are you going to do then? Okay, you're not going to sample all 100. Once you get to large numbers like that, then you're going to be getting the same answer 100 times, plus or minus some uncertainty. So that's too expensive. You're wasting your time. Once you've characterized these 100 packets, after about the 25th one, analyzing the other 75 is a waste of time and a waste of money, okay? Because you've characterized it. So how would we decide? Well, we would sample the first 20 and then 10% of the remaining ones. So if I had 100 samples, the first 20 we would sample, and then I have 80 left. And so 10% of 80 is 8. So I'd sample 28 out of that pack of 100. And that saves a lot of time, but yet I've analyzed it and I've characterized it, and I know that grouping if there's no visual difference between the two. And so I think this is the key. If I've got a trunk load, little whatever they call them, dime bags or something like that, and they are all exactly the same packaging, exactly the same consistency, then if I've got 300 of them, okay, I sample the first 20, first meaning random, draw 20 out randomly, and then 300 minus 20 is 280, 10% of that is 28, and so I've got 20 and 28, I've got 48 samples out of that 300, okay? But that's if they all look the same. What if I look at that and I say, I've got 100 that are in blue bags, but yet the powder looks similar, but 100 in blue bags and then 200 in clear bags. Well, there's a visual difference there. And so I really have two seizures. I have a seizure of blue bags and I have a seizure of clear bags. And so I need to do two separate sampling plans. But even then it comes out being okay. So the 100, there I've got 28 to sample. And then out of the 200, I'm going to have the first 20 and another 18. So 38. So I have 28 and 38 in that situation. So it's more because I have two different seizures, but it's still not 300. And so that's the key. And it's a little more conservative than what I would get from the ASTM standard. So I'm sampling a few more bags, so I'm on the conservative side, but it's also very easy to calculate. We were able to calculate these sampling plans in our head, just using 10% of the remaining. So I think it's a good rule of thumb if you don't have other guidance. Now, if you get into a crime lab or an analytical lab of some sort and they have a sampling plan, you would follow it. But I just wanted to give you some rules of thumb, and this one would be one that you could use. If they don't have a sampling plan and they just kind of fly by the seat of the pants, you can add something to the process and say, look, let me find those notes that Williams gave me. And so, but basically this is what we just talked about. So before we get into the Minitab stuff, let's do a Kahoot. Codes are getting longer. I think more users are using Kahoot.
Success.
That's
Attachments are working.
That's right.
Those are very satisfying.
It's what?
That's a very satisfying image.
Just a lot of those double numbers. All right, so we have 5, 10, 15, 20. Looks like everybody's in. Oh, we lost some.
It's not letting you.
No, it's doing the same thing again.
Oh no.
I'll join in on like the second question.
Okay, very good.
Robin, are you on the app or are you on?
I'm in like the online thing.
Download the app
Yeah.
because it used to be next to me in PK. I can download it.
Oh really? Okay.
Well,
Yeah. All right. Anybody else waiting to get in?
I'm not in
Okay.
there. In there.
Yeah, I know. My old phone was so full of stuff. Okay, let's go. Sorry, Rob. catch it. All right, just 5 questions. I'm gonna try to increase the text. There you go, that's a little better. All right, so 3 of those I would say are, fair answers. Pick your favorite, Once again, pick your favorite. So this is the outlier test. That was that result of 15 in the trainees data set. Good. Remember, the F test is for equal variances. Okay, so determining if the 2 means of the 2 sets are equal, which one would you use? That's weird. Oh, you must have gotten in.
Yeah, I'm in now.
It's waiting for you to answer. There we go. All right. So the t-test for equal means. You know what the next one's going to be, I'm sure. Test for determining if the uncertainties of 2 data sets are equal. Yeah. Ready to go. All right, very good. So the F test for equal variance. Someone has a streak. Which of these options is not a good sampling plan? Not a good sampling plan. So the first one is test 10% of all the drug seizures. Test all of the first 20 packets, and 10% of the rest is blue. Orange is test all packets, no matter how many there are. And then green, do whatever the gum or ASTM 122 suggests. Pick your favorite. And I posted the gum on Blackboard, or at least an older copy of it, so you can kind of see it's very detailed. Several hundred pages. All right, so again, which one of these is not a good sampling plan? You're either testing all of them, no matter how many there are. Why would that not be a good sampling plan? I mean, you're testing everything.
5,000
Yeah, exactly. That was one thing that I always struggled with as an undergrad, in instrumental analysis. I was like, let's just do ICP-MS on everything, and then I always got points off because it was too expensive. Like if a $2,000 flame AA would work, or 12,000, let's be realistic, 12,000 versus $300,000 ICP-MS. Just then use the flame AA, right? And I was that drove me crazy. It was like, no, use the biggest and best, most crazy NASA instrument and everything, and then testing 10%. Why would that not be good? It's too few, yeah. It's like you get 10 packets in, it's like, okay, I'll just test 1 and call it good. Probably not a good plan, right? So, eventually you need to test, a reasonable amount, and that's what these others would be good. So, okay, a little Mario Kart dancing. Okay, dun dun dun. 5,000 points. Yay, confetti. I still miss the little cloud guy with the.
really close up.
Yeah, no, man, look at that. Milliseconds.
Yeah.
Yeah. Yeah. It's so frustrating too. You got a good streak going, and then all of a sudden the phone does something weird. Yeah. Okay, so let's look now at some of these similar analyses, but using Minitab. Yes.
So, my question was, if they like tell you on the, like whatever the drugs that you get, that it was all from the same seizure,
Mm-hmm.
but like say the drug dealer used like rainbow bags, do you have to separate them by the bag?
Yeah. Again, it would be a management decision. I mean, y'all would decide what to do and document it. Yeah. But let's say you get in there and you start doing the analysis and you say, well, these bags are the same, right? There's really no difference. And your data is crazy. You're going to have, hopefully, recorded, these were the blue bags and the yellow bags and the green bags and so on. And you'll say, look at this, if we block this by bag. So if you got, think about Excel, you've got a column of bag color and you've got a column of your analysis results. And you can then do in Minitab, you can say, what is the mean of this column? And it'll tell you the percent, cocaine or whatever. You say, now what is the mean if I use the bag color as a group? And it says, okay, the blue ones have this mean, and the green ones have this mean, and the yellow ones have this mean. And you could do t-tests on those means if you wanted, or you could just look at them and say, wow, they're all pretty much the same, or they're dramatically different. So sometimes you would say, well, let's sample 20 of them, see what we have. And then if we need to split them out, we'll make that decision. So that's how I would handle that situation.
So,
Does that answer your question? Yeah.
So would you want to just do like more qualitative qualifiers on your data and then separate it out later?
Well, it would help. The more information you have, like on your sample recording sheet. Now that's another thing that we really haven't seen in academia. In your labs, you don't have a data collection sheet. So what you would have is some sort of descriptions of the sample, how they were prepped, what solvents you used, and so on, case number. So you would have this paperwork that goes with the different samples. And so that would be entered into the computer, and then you could block the data by these other factors. So you have as much information as the analyst puts on those sheets. And if you train your people to put everything they have on those sheets, then you can go back and see if there was an issue or not. Or if you can do like start the analysis and see if there's an issue and then change your plan to take it into account or not. Yeah, that's a good question. That all those Excel formulas I put in there just so that you could do these things in Excel, because sometimes you do have to build your own analyses. But Minitab has a lot of very nice things. So we did that outlier test, and Minitab, you just take that trainee data and do a graphical summary, and it tells you there's an outlier. See the star? So that's a histogram of the data, and you see that data point at 15, and it has an asterisk underneath it. It says this is an outlier. Okay. It's giving you the mean and standard deviation and everything over here. It gives you the confidence intervals for the trainee, and you can see that they go from 13.5 down to 12.2, just like we calculated. Here's the analysis for the forensic chemist. Notice the trainees' data looks all more clustered and so on, but it's misleading because the x-axis scale has changed. The far left is like almost 11 and a half, and the right is 15. Look at the forensic chemist. The left is 13.1 and the right is 13.7. So even though the data is not normally distributed, up here we have a p-value for a normality test. So this saying is the data normally distributed, there's a 1.7% chance that the data is normally distributed, okay? And it's just because they got the same answer a couple of times. The 13.1, they have a few data points where that was the answer, and the 13.2. And so again, if it's normally distributed and you have another decimal place, then you wouldn't have those numbers right on top of each other. So it's not an indictment of the data and saying it's bad, it's just saying it's not normally distributed. And it's really a function of only calculating 10 of those values. So how do we get to those? Here's the menu structure in Minitab for calculating the two-sample t-test. So this is really helpful if you do download the mini tab. You have the basic statistics, stat menu, basic statistics, 2 sample t-test, and you have the samples in different columns. You have the trainee column and the forensic chemist column, and then you can put up some plots and do the t-test. Here's a box plot that you get from that. You see the trainee on the left and the forensic chemist on the right. Now I like this because it's really visual. So if you're going to show somebody, say in management, these are our results, they could look at this and say, wow, the forensic chemist is a really tight data set and the trainee is really spread out. But the means are pretty close to each other, meaning the boxes overlap. So just this one chart can tell us just about everything that we concluded from the numbers. That the means are about the same. They're not statistically significantly different because the boxes overlap. Those boxes are the quartiles. So 25% of the data is below the box, 25% of the data is above the box, and the box contains the middle 50%. And if those boxes overlap, it's saying that the trainee and the forensic chemist have pretty much the same answer, the same means. But if the box and whiskers, those little sticks coming out are whiskers, so these are box and whiskers plots or box plots, if they're dramatically different in their size, they have different variances. Okay. So this shows that the trainee is much more uncertain in terms of their data. This is an individual data plot. So this is showing you every data point for the trainee and every data point for the forensic chemist. And you see the forensic chemist had 3 data points that were the same answer and 4 data points that were the same answer. And that's why that's not normally distributed. And the blue dots are the mean values and the line just shows you visually, how they're connected. So if that line was horizontal, they would have exactly the same mean. I think this box plot is a little more useful than this, but this is nice because it shows you the individual measurements plotted next to each other. This plot is pretty difficult to do in Excel. This one you could do, but again, generating these things is a pain in Excel. There's a lot of steps involved, whereas here it's just a menu option. Click, 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 you've got it. Here's the F-test, comparing for equal variances. And this is kind of nice because you go in and you say 2 variances, you tell it trainee, forensic chemist, and calculate the test. And this gives you the probability that your null hypothesis is true. Remember our F value, our fraction was 21, and our critical value was 4. Okay. And so this isn't saying that there's 0 probability, it's saying there's 0 probability to 3 decimal places. All right? So it could be 4 in the 4th decimal place. So we know it's less than that. Okay. But we're pretty confident here because what's the null hypothesis? That they have the same variance, and that's the probability that they have the same variance. So it's 0 to 3 decimal places. This is kind of nice too. I don't know some of these things, like I don't know what the Bonferroni confidence interval is for the standard deviations, but I do know what a confidence interval is, right? And so here's the trainee's standard deviation, and this is the actual confidence interval for that standard deviation. So don't let that blow your mind, okay? We've been doing confidence intervals around a mean. So here's the mean, plus or minus. So I'm saying that the true mean is somewhere between these endpoints. This is a confidence interval on the standard deviation. So yeah, it's really weird to think about, but it's the standard deviation of the trainee, and the true standard deviation for that person is somewhere between these 2 limits. Okay, so they could be worse than this, or they could be better. Okay. And then the forensic chemist, that's their standard deviation and the confidence interval for their standard deviation. So on their worst day, their standard deviation is still less than 0.5, okay, of a percent. Even on a bad day, they're really good, yeah. And the trainee's like, dang, even on my best day, I'm not as good as that person, yeah. So, somebody that needs to be brought along and trained. I don't know if it's their technique or what. Or if the test was rigged and the forensic chemist said, you use that GC. Yeah, the one with the big hole in the insulation, and the temperature controls all over the place. Okay, so for homework, you can repeat all of those Excel calculations, and then if you download the free trial for Minitab, you can go and try these same things in Minitab for the data. So the data's right there in Excel. You just type in those 20 numbers and you're good. Okay, and you know all the answers because they're right here in the notes. So it's not like trying to say, do this, but try to put your mindset in to this, to do it without constantly looking at the notes. Okay, try to figure out how to calculate all those values, and you'll be great. Now, one thing that I skipped over, let me zoom way back, and this is a nice little pro tip in Excel. I don't think I should really emphasize this in PChem much, but it is being able to make a cell do this right here, that range. Look, that's a number, a space, a dash, a space, and another number. How do you do that? Okay, well, I've shown you right here. Okay, it's called concatenation, and you can use quotes and ampersands to make up basically a dynamic cell that has text in it. Okay, you can use plus or minuses in there. You can use units like angstroms or what have you, and you can build that up using ampersands and quotes. So this right here is saying round the let's see, what are we talking about here? This is the range. Okay, so round that low value to 1 decimal place, close parenthesis, and I put that ampersand and an open quote. So I can type in space dash space. So space dash space is just text. I could write any kind of text in there. I could put the plus or minus sign in there or whatever. And then I close that quote, do another ampersand, the and symbol, okay? And then I round the upper value, the mean plus the half the range, and round that to 1 decimal place and close that. And so that's how I got these little cells to show the 2 different numbers with a dash and some spaces. So that's a really handy tool if you're building reports in Excel, because not every lab is going to have a laboratory information management system, a LIMS, that generates reports. If you have to generate your own reports, this little trick here is going to be super helpful. You want to say 95% confidence interval equals, and then you want to have the mean, and you have it say plus or minus, and the standard deviation times 1.96. You can put all of that in one cell, and you don't have to type anything. So when you put in new data up here and you do all your formulas update, that 95% confidence interval updates too. And it all looks very nice. Okay. So sort of a closing pro tip. All right, we'll see you next time.